Imagine tossing a coin. You expect it to land as either heads or tails, right? But what if it could be both at the same time? Welcome to the perplexing world of quantum gravity. Now, let's take a brief dive into this fascinating universe. Quantum gravity is the field of theoretical physics, attempting to reconcile the theories of quantum mechanics and general relativity. It's like trying to blend oil and water. They're both liquids, but they just don't mix easily. Quantum mechanics is the realm of the infinitesimally small. It describes the bizarre and counterintuitive behavior of particles at the atomic and subatomic level. It's a world where a particle can be in two places at once, and reality doesn't exist until it's observed. On the other hand, general relativity, the brainchild of Albert Einstein, governs the massive. It explains the behavior of planets, galaxies, and the universe itself. It describes gravity not as a force, but as the curvature of space and time around massive objects. Imagine placing a bowling ball on a trampoline. The ball creates a dip, and that dip is what we perceive as gravity. So here's the rub. These two theories, quantum mechanics and general relativity, describe our universe perfectly in their respective domains. But when it comes to explaining gravity at the quantum level, they clash. Is gravity a force carried by particles, as quantum mechanics would suggest? Or is it the warping of space-time, as general relativity proposes? This contradiction is the heart of the quantum gravity enigma. It's possibly the biggest unsolved puzzle in theoretical physics, and it's stirring up a storm in the scientific community. The goal is to find a theory of quantum gravity, a theory that can describe gravity within the framework of quantum mechanics. So, is gravity a particle or a wave? That's what scientists are trying to figure out. Now picture this. You're at a party with a room full of people, but you can only see one person at a time. That's quantum mechanics for you. Quantum mechanics, the theory that describes the smallest particles in our universe, is a bit like this party. It's a realm where the usual rules of physics just don't apply. You know, the kind of party where anything goes and you're never quite sure what's going to happen next. Take superposition, for instance. It's a principle that allows particles to be in multiple places at the same time. Imagine being able to dance with everyone at the party simultaneously. You're not just on the dance floor, but also lounging by the snack table and even outside under the stars. In the quantum world, particles can do just that. They exist in all their possible states at once, until someone or something interacts with them, and then they choose a single state. Now let's add another twist to our party. Suppose you meet someone and hit it off. You dance, you laugh, you share a few jokes, you're entangled. In quantum mechanics, entanglement means that two particles become linked, and whatever happens to one instantly affects the other, no matter how far apart they are. It's like knowing exactly when your dance partner is going to spin or dip, even when you're on opposite sides of the room. But here's where things get really wild. These quantum particles, they don't just affect each other. They're influenced by everything around them, by the entire universe. It's as if the music, the lights, even the mood of the party can change the way you dance. Quantum mechanics is a wild party indeed. It's a world where particles can be in multiple places at once, where they can influence each other across vast distances, and where the dance of existence is shaped by the universe itself. But how does gravity fit into this picture, you might wonder? Well, that's where things get even more interesting as we venture into the realm of quantum gravity. But that's a story for the next scene. Imagine you're rolling a ball down a hill. It's predictable and straightforward, right? That's how gravity works according to general relativity. In this scheme, Albert Einstein, the man behind the theory, envisioned our universe not as a flat plane, but as a fabric of space-time. Picture a rubber sheet stretched taut. This sheet represents our universe. Now, if you place a heavy object on this sheet, like a bowling ball, the sheet will dip under its weight. This dip, this curvature, is what we perceive as gravity. So if we return to our ball rolling down the hill, in the realm of general relativity, that hill is actually a dip in the fabric of space-time caused by a massive object. The ball isn't so much rolling down a hill as it is following the path that's been curved by the weight of the object. This is a far cry from the classical Newtonian view of gravity as an invisible force pulling objects together. Einstein's theory also introduced the concept of time dilation. This means that time itself can speed up or slow down depending on the intensity of the gravitational field. It's why time runs slightly slower for someone at the base of a mountain compared to someone at the peak. Yet, despite these mind-bending ideas, general relativity is very predictable. The paths that objects will follow, the rate at which time will flow, it can all be calculated with precision. This predictability is what makes general relativity so useful in fields like astronomy and GPS technology. However, there's a catch. While general relativity works perfectly with large objects like planets and stars, it falls apart when we go down to the very small, the quantum level. Here, particles don't follow smooth paths. They pop in and out of existence. They can be in two places at once. They are anything but predictable. In the world of general relativity, gravity is a smooth, predictable force. But can it really be that simple? So we have a wild party on one hand and a predictable hill on the other. How do we bring these two together? Well, that's precisely the quantum gravity challenge. It's like trying to get a square peg into a round hole. Or to be more accurate, it's like trying to merge the wild, unpredictable world of quantum mechanics with the smooth, predictable realm of general relativity. The challenges are manifold. Primarily, the issue lies in the fact that quantum mechanics and general relativity operate on fundamentally different scales. Quantum mechanics is all about the very small, think atoms and subatomic particles, while general relativity is about the very large, think planets, stars, and galaxies. Bridging the gap between these two scales is no easy task. Scientists have made some progress though. They've developed quantum field theory, which applies quantum mechanics to fields rather than particles. This has been successful in describing 3 of the 4 fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. But gravity, the 4th force, has proven to be a stickler. Then there's string theory, a candidate for a quantum gravity theory. It proposes that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings. This theory has shown promise in unifying quantum mechanics and general relativity. But it's not without its problems. For one, it requires the existence of extra dimensions, which we have yet to observe. Despite these efforts, a complete theory of quantum gravity remains elusive. The theories we have so far are either incomplete or unconfirmed, lacking the empirical evidence needed to fully endorse them. But that's not to say it's a lost cause. Far from it. The quest for quantum gravity is like trying to smooth out a wild party or bring some unpredictability to a smooth hill. It's a fascinating challenge that continues to perplex scientists. And who knows, perhaps one day we'll finally find the key to this cosmic conundrum. Remember the coin toss? What if understanding quantum gravity could help us predict the outcome? You see, quantum gravity is like the secret sauce in the cosmic recipe, the missing piece of the puzzle that we've been trying to fit into our understanding of the universe. Think about it this way. We know how gravity works on a grand scale, governing the orbits of planets and the dynamics of galaxies. We also understand the quantum world, where particles can be in multiple places at once and affect each other across vast distances. But how these two realms intersect remains a mystery. So why does it matter? Why should we care about a theory that's still in its infancy, that's yet to be proven? Well, for one, quantum gravity could help us understand the origins of the universe. It could shed light on the Big Bang, the moment of creation, and what came before it. It could also explain the nature of black holes, those enigmatic objects that seem to defy the laws of physics as we know them. But beyond these grand cosmic questions, understanding quantum gravity could also lead to practical applications. Just as the theories of relativity and quantum mechanics have given us GPS technology and computers, Who knows what quantum gravity could bring? Faster than light travel, perhaps? Quantum computers that make today's supercomputers look like abacuses. The possibilities are as vast as the universe itself. The journey towards understanding quantum gravity is not just about finding the missing link in our cosmic understanding. It's about pushing the boundaries of human knowledge, about venturing into the unknown, and coming back with insights that could revolutionize our world. As we continue to explore the enigma of quantum gravity, who knows what fascinating truths we may uncover about the universe and ourselves.